Okay, to calculate C then, in this situation, so to find C, and it's the same in any situation involving integration, to get this function that's going to be useful, it's no good to us if we don't know what C is. I can't find out what the work is done if I don't know C. So what I need is a set of conditions, and we always have this problem. They're called initial conditions or boundary conditions sometimes. In other words, I need to know for a given point on the curve, this curve here, a given point, what is K, what is the work done, and what is the extension. So let's say I did an experiment with this spring, and I found out that I need to do 62.5 joules of work to extend it 12 millimeters with a spring constant of 0.5 newtons per millimeter. Those are my initial conditions. Now if you look at it, that means I can put K and X and W into this. I know those three, so that means the only unknown now is C. I can calculate what that is. So that's just exactly what I do. I put in my values for W, K and X. So underneath I write W, which is 62.5, equals a half times K, which is 0.5, times X, which is 12, squared, plus C. And then I work out what C is. Well, a half times a half is a quarter. 12 is 144. So that's 144 over 4 plus C. Then I can get a calculator out to work this out. Does that go? It does, doesn't it? Fours into 14 goes 3, remainder 2. 4 into 24 goes 6. That's 36 plus C, if I'm correct. So I'm solving this little equation, and you'll have to do something similar. So now to get C, subtract 36 from both sides. So what does that leave? 24, 26.5. So C is 26.5. I found out what C is. That's the only way I can do it. I need to have some initial conditions, and then I could calculate C. So now I've got my formula for work. But what does C represent? So let's write down our formula for work now. Work equals a half K X squared plus 26.5. That's our formula for the work. So just to recap, we've put in some values and we ended up with this formula for work. Here it is. Now what we have to do is think back now to our original problem, which was this spring here, this original situation, and think about what this 26.5 represents. What does it mean? And it always has a meaning when you find it, because we're applying this integration to an engineering situation, and even if the question you're asked isn't directly associated with an engineering situation, C always has a meaning. And in this case, to answer the question, what does this 26.5 mean, you ask yourself, what happens if x is 0? If x is 0 in this formula, in other words, right at the beginning, if x is 0, all of this disappears. So that means the left-hand side, which is work, equals 26.5. So it's saying that the work that we've done is not 0 at the beginning. It's 26.5. So if you think about it, it must be a situation where we're starting here, say, and the spring is already extended by a certain amount. And we're interested in what happens after that when we extend it further. In other words, it's preloaded. So what does this 26.5 represent? It represents the work when x is 0. In other words, the work at the start. We've had to do 26.5 joules of work to get the mass to this point, and then we're going to extend it further, and then this graph will tell us what that work is. And if you look back to the original graph, that would be the 26.5 mark, so it's not quite at 0, it's starting a bit further up. Sorry, that would be this area here rather, not that point, the work done to get us to that point before we start.